Hi, welcome to Lab 3, the black hole orbit. In this lab, we were to find the mass of a black hole. We were given the mass of the star that is orbiting it, the time step, and the position of the black hole. More important than the mass were the methods that were used to find the mass, including Newton's second law, the momentum principle, and Newton's law of universal gravity. The solution that I found was that the mass of the black hole was 5.18 times 10 to the 31st kilograms. This is over 10,000 times the mass of the star that we were given. We were to take the information that we were given and insert it into the Python program so that we could find the mass of the black hole and have a display to show what the star orbiting looks like. On the left, you can see that the mass of the star that I was given is 5.0231 times 10 to the 27th. The time step that we were supposed to use was the length of 1 day, and the position of the black hole was inserted up here as the vector 3 times 10 to the first, 1 times 10 to the first, and 0. We altered the information in Python, and first we changed the y component of the velocity so that it would match the x component of the velocity. Next, we moved to the calculation loop. Here we have that the velocity initial and final, and the momentum initial and final, which is just found by using the star's mass times either the velocity initial or the velocity final. Delta V and delta P are both found by subtracting the initial from the final. Here we have that dP dt is equal to delta P over delta T, and that F net is equal to dP dt. We will explain why this is okay later. When we are trying to find dt dt parallel, we first have to find the direction. This is just found by finding the initial divided by the magnitude of the initial, which is the unit vector. D magnitude of P over dt is equal to the magnitude of P final minus the magnitude of P initial over delta T. This is alright because in the formulas that we learned in class, we see that dt dt parallel is equal to d magnitude of P over dt times P hat. This can be broken down into simpler solutions, finding that eventually we get to the magnitude of P final minus the magnitude of P initial divided by delta T, which is shown here in this formula. dt dt parallel is equal to the magnitude times the direction, which is also shown in the formula that we learned in class. We set the F net parallel to dt dt parallel just as we did with the F net. When we are calculating dt dt perpendicular, we already know the total dt dp, and we can simply subtract dt dt parallel. Again, we set the F net perpendicular to dp dt perpendicular. In order to find the mass of the black hole, we wanted the program to do all of the work for us. We set in the formulas that we learned, we know that the F net is equal to the gravitational constant times mass 1 times mass 2 over the magnitude of the radius squared. Here, since we are given the mass of the star 1, the net force, and the radius, which is simply the position of the star minus the position of the black hole, we can solve for M2. M2, which is going to be the mass of the black hole, it looks like the magnitude of the net force times the magnitude of the star's position minus the black hole's position squared, because that's the radius, divided by the gravitational constant times mass 1. This was simply found by rearranging this formula here. In our Python program, we have it written here, where the magnitude of the net force times the magnitude of the star's position minus black hole position squared divided by the gravitational constant times the star's mass. The gravitational constant was inserted first so that the program would know what to do with it. Here we have to print the black hole. If I had done this after the loop, such as where it's hashtagged here, then it only would have printed out one value. But now, as you can see, the program will run and the value of the mass shows up here, which is fairly constant the whole way, and gives us a value of 5.18 times 10 to the 31st. In the visual model, we can see that here the black arrow is the net force parallel, or is a dp dt parallel. The yellow is the dt dp perpendicular, and the red arrow here is the net force, which is going towards the mass of the black hole. We can set the net force to dp dt and everything else like that because the net force and dp dt are the same numerically. The difference is that dp dt is the cause of the motion. We can observe the changes in the momentum and time, while the net force is simply the effect of the motion. It is the force behind the movement. The what-if question asked us to imagine a different black hole mass that was placed in the same place. The motion of the star remained unchanged. Could it be possible that you get a different black hole mass for the same trajectory? The answer to that is no. With gravity being the only force on the star, if the trajectory was the same and the positions were the same for every single point, the mass could not be different of the black hole. Finally, summing everything up, our final answer was that the mass was 5.18 times 10 to the 31st kilograms, and this was found by using the momentum principle in Newton's second law and the universal gravitational law.